Welcome to the Research Cortex's AACTO Abridged, video supplements to our original articles. Today, we will discuss Rachel Traylor and Jason Hathcock's work, Vertical Dependency in Sequences of Categorical Random Variables. This paper is an extension of the previous work by Traylor, a generalized multinomial distribution from dependent random variables. You can either visit the Research Cortex, or if you're watching this through YouTube, see the description for a link to the previous paper's AACTO review video. This new paper contains three main results. First, the notion of sequential dependence for random variables is defined. Traylor and Hathcock showed that sequentially dependent categorical random variables, like the first kind dependent random variables from the previous work, are identically distributed but dependent. Second, the pairwise cross-covariance matrix for two categorical random variables in a sequence of sequentially dependent random variables is obtained, and the formula is actually quite interesting. The third result, and the pièce de résistance, if you will, of this paper is the creation of a class of functions on the natural numbers that generate dependency structures, like the first kind dependence we've seen before and the sequential dependence we'll see shortly. Any dependency structure generated by a function in this class retains the identically distributed but dependent property. Don't worry, we'll look into each of these in turn in a bit more detail. It's actually much simpler than you think. Let's do a brief review of first kind dependence from the previous work. So the graph that you see here shows the dependency structure. This first variable, which is right here, so this epsilon1, is a typical categorical random variable with three categories in this case. So 1, 2, 3. Here's its possible outcomes. Each of these outcomes has a particular probability of occurring. P1 for 1, P2 for 2, and P3 for 3. So this first line, remember, this is basically epsilon1, and these are the possibilities 1, 2, and 3, with its corresponding probabilities on the line. Now the second random variable, so here's epsilon2, and this next level of the tree belongs to epsilon2. This one depends on the first variable, and what do we mean by that? We're going to weight the probabilities of the three possible outcomes of epsilon2 towards the outcome of the first variable, epsilon1. So what do we mean by that? If epsilon1 picks a 2, so that means we're right here on the tree, then epsilon2 can take on values 1, 2, or 3. But here I'm actually going to weight the probability of epsilon2 picking a 2 by a little bit more, and then weight the other ones a little bit less to make up for the fact. So that means if epsilon1 picks a 2, then it's slightly more likely that epsilon2 will pick a 2. Now, just as another quick example, if a 3 came out of epsilon1, then we'd be on this part of the tree. And again, epsilon2 has three possibilities, 1, 2, and 3. And we weight towards the 3 here and away from 1 and 2. So if the first one comes out to be a 3, then epsilon2 is slightly more likely to pick a 3, depending on the level of your delta. If delta is equal to 1, then it's deterministic. Then if epsilon1 picks a 3, epsilon2 will definitely pick a 3. So again, refer to the previous video for a more detailed explanation. I'll link that as well. So what does this also tell us? By moving down this tree, we're actually creating a sequence. So let's say epsilon1 is 1 here, and epsilon2 comes out to be a 2. Still possible. So then, by moving from here to here, we've created a sequence of length 2 with the outcomes 1, 2. So epsilon was 1, epsilon2 is 2. And the probability of that occurring is P1 times this P2 minus. So remember that delta is our dependency coefficient, and it takes on values between 0 and 1. And since we're on three variables here, Pi plus, that's basically weighting towards that outcome I, and that's defined as Pi plus 1 minus Pi, so everything else, times delta, and Pi minus is equal to Pi minus delta times Pi. So just to remind you what all of those are, and in this case I is going from 1 to 2 to 3. Now at the third level, again, let's look at this third level. The outcome of the third one is weighted towards what happened in the first one here, and that's what I want to point out because we're going to be looking at sequential dependence, which is quite different. So if the first one is a 1, we weight towards a 1. And this one seems natural because, say, the second one was a 1, too. But if the third one comes out to be a 1, even if the second one was a 2, right, we're on this P2 minus, this is still a P1 plus because we're on the level of P1. Epsilon 1 was 1, and therefore we're still, even though epsilon 2 was 2, we weight towards the outcome of the first one, which is a 1. Just to show you on a different part of the tree, let's say epsilon 1 comes out to be 3. Then if we jump down to this third level, no matter which branch of, which split of epsilon 2 we get, right, we're still weighting towards 3 because that's what the first one was. Let's now move towards the sequential dependence. So this is our new form of dependence. So this tree looks quite similar, but we're going to weight the next variable towards the outcome of the previous variable, not necessarily epsilon 1. So to really see this, let's jump down to the third level here. So here we go. Now let's take a look here. This one hasn't really changed, but this node here, epsilon 1 is still 1, and epsilon 2 is 2. Now in the previous case, because epsilon 1 was 1, we didn't care what epsilon 2 was, so we weighted towards epsilon 1, which in this case would be 1. But now, instead of this being a P1 plus, this is a P1 minus. We weighted towards the outcome 2 because epsilon 2 was 2 in this node. So it doesn't matter what epsilon 1 was in this case. Every time epsilon 2 comes out to be 2, we weight epsilon 3 towards 2, as an example. So we only look one step back at epsilon 2 to decide the weights. So let's do a quick example that really illustrates the difference between sequential dependence and first-kind dependence. Let's say we want to figure out what the probability is of the sequence 1, 2, 1. Alright, so let's first do, so what is the probability of this? Let's first do this under first-kind dependence. So for first-kind dependence, the probability of the sequence 1, 2, 1 is going to equal P1, right, because that's the probability epsilon 1 equals 1. Now, the second one is going to be P2 minus because this is a different outcome than 1, so we need to weight away from that happening. And the third one is 1. Now, in first-kind dependence, we weight towards the first one, so this is P1 plus, right? We're weighting towards the first one. Sequential dependence, the probability of that same sequence occurring, but if we change the dependency structure, well, P1 doesn't change. And 2 is not the same as 1, so we need to weight away from that. Now, in this case, the third one, we need to look one step back. Now, 1 is not the same as 2, so we need to weight away from that. So this is P1 minus. So notice the difference here. This versus this. Here, we were looking back at the outcome of the second one, which was 2. Therefore, they weren't the same, and we weight away from 1. Here, we had to look back at the first one. So 1 is 1 over here. So epsilon 3 is 1, looks back at epsilon 1, which is 1. Therefore, we weight towards 1, and that's why you have the plus here. The first theorem proven in the paper says that even though we've changed the dependency structure, sequentially dependent random variables remain identically distributed. And what I mean by that is the probability that any random variable in that sequence is equal to a particular I. So remember that I goes from 1 to k. So this is your number of categories, which was 3 with our trees, is going to equal pi. So no matter which n that is. Now this is different than the conditional probability that we looked at before. So the conditional probabilities say the probability that epsilon 2 equals I given that epsilon 1 equals the same thing was pi plus. Or if it wasn't the same, that's conditional probabilities. That's the fact that they are in fact dependent. But if we want to look at the unconditional probability, what's the probability of this occurring at all, right? Over all the possible sequences there, what is the probability that of all those possible sequences, the nth one is I? It's still the same. They're all identically distributed. Alright, so why should we care? Let's pause and talk about that. First, many other random variables are functions of these base random variables, But we usually assume that the base random variables are independent and then take functions of those. So, for instance, the sum of Bernoulli random variables gives you a binomial random variable. And they assume that they're independent, and so that sum gives you a binomial random variable. So Korzeniowski, and again see the previous paper for this, showed that these Bernoulli random variables, there's an R there, can be dependent and still yield a generalized binomial distribution. So the sum of that, we can actually look at the distribution of that, and it looks pretty similar to a binomial distribution. The previous paper did the same thing, but with categorical random variables. So the sum of first-kind dependent categorical random variables yields a multinomial distribution. That is a generalized version of the previous one. So now that we looked at sequential dependence, and we'll look at another class of them, we can start looking at functions of random variables under different dependency structures to see what kinds of distributions can come out. And the other one that's got a more applied bent, the notion of independence is rife throughout assumptions in statistics, in particular regression. We assume that error terms are, normally distributed, but the subtle one and the most important one is that they're independent and identically distributed, namely independent. And we make this assumption because the math is easy. There's a lot of properties that fall out quite naturally with IID random variables, things like that. And so we have to contort ourselves an awful lot in data science to force real data, which is unlikely to be independent, to fit this framework of rather restrictive assumptions. And this paper is important because we haven't had the mathematical framework to deal with actual dependence in a formal manner until now. The next result involves the cross-covariance of dependent categorical random variables. So remember that this is a generalization of sorts to the idea of covariance between two Bernoulli random variables. So the paper discusses it for categorical random variables, but here I'm just going to take the special case of two categories, which gives us a Bernoulli random variable, and show the pairwise covariance under first-kind dependence and sequential dependence. This will still give you the idea, but we don't have to deal with a whole bunch of matrices. So let's look at first-kind dependence first. So this was in the previous paper, and it's also in Korzeniowski's original work that's cited in both this paper and the previous one. So under first-kind dependence, the covariance between any two So the covariance between the first variable in a first-kind dependent sequence and any other is p times q. Now remember that q is 1 minus p times delta. And the covariance between any other two is pq delta squared. All right, so this guy, right, anything but 1. So for example, quick example here, under this, the covariance between epsilon 1 and say epsilon 3 is equal to p times 1 minus p times delta, where p is the probability that epsilon 1 equals 1, and 1 minus p is the probability that epsilon 1 equals 0. And the covariance between epsilon 2 and epsilon 3 is equal to p times 1 minus p times delta squared. Now, if we look at sequential dependence over here, then the covariance of any two sequentially dependent Bernoulli random variables is pq delta to the n minus m. So this is the interesting result here. So m can be 1 in this case. And what I want to point out here is that this is essentially the distance apart that these two variables are in the sequence. So for example, covariance of epsilon 1 and epsilon 3 under sequential dependence would be p times 1 minus p times delta squared. And the covariance between epsilon 2 and epsilon 3 is p times 1 minus p times delta. Now, right, again, if we kind of write out like epsilon 1, and then epsilon 2, and epsilon 3, and epsilon 4, and so forth as our sequence, then, well, what's the difference? The covariance between epsilon 1 and epsilon 3 goes in powers of delta as the distance increases. So what is this actually telling us? In the case of sequential dependence, the further apart they get, the less correlated these two variables are. Now that correlation will still be there. It just might get very, 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 very small. So this is unlike first kind dependence, where it's pretty fixed, right? It's either as a factor of delta or as a factor of delta squared. Here, as you get further and further away from a particular fixed one, you approach independence of those two. All right, let's now move on to the main event. Traylor and Hathcock defined a class of functions, and I'm going to write the class of functions and we'll talk about it. So this is a class of functions that map naturals that are at least 2 to other natural numbers, such that alpha of n is less than n, and alpha is dependency continuous. And we'll talk about each of those things real quick. All right, so first, these are functions that map natural numbers to natural numbers. And this is basically mapping an index to another index. So what does epsilon n depend on? So epsilon n depends on epsilon alpha n. So for a quick example, for first kind dependence, alpha of n is 1, meaning that every single epsilon greater than or equal to 2 depends directly on 1. For sequential dependence, alpha of n equals n minus 1. So the third one depends on the second one, the fourth one depends on the third one, and so forth. All right, and then the last thing is, what do we mean by dependency continuous? Well, I mean that for any n, it has to map somewhere. So you can't skip one. That means that 2 has to map to 1 because it has to be less than n. 3 has to map to either 1 or 2. You can't just leave 3 by itself and have it map to nothing. 5 has to map somewhere from 1 to 4, right? You can pick whichever one you want, but it's got to map somewhere. Now, any function in this class will generate a different dependency structure, just like these two examples right here generated first kind dependence and sequential dependence respectively. And what was proven in this paper is that any function in this class generates a sequence of identically distributed but dependent categorical random variables. I can guarantee you that any structure that you come up with a function in this class retains that identically distributed property we mentioned before. The next couple slides I'll show you are some graphical representations of some examples of functions in that class and the dependencies they generate. The graphical representations will be nice because we can actually notice a couple other fun patterns. So let's start with this first one. This guy's just first kind dependence. First kind dependence. And if we look at generating a graph where a node represents, some epsilon, and then we draw an arrow to the thing it depends on, everything points back to 1 because everything depends straight on 1. You end up with this nice little circle. Notice that, again, there's always a path to 1, which actually is a kind of a visual way to see that all of these have to be identically distributed. If 2 is identically distributed to 1, and 4 is identically distributed to 1, and anything with a path to it is identically distributed to 1, well, they all have to be identically distributed because they all connect to 1. Here's sequential dependence. Here's this nice graphical representation of sequential dependence. So 2 depends on 1, 3 depends on 2, and so forth. Again, now there's always a path from any n I pick all the way back to 1. Now it's in multiple steps, and here you can actually see that nice property of the cross-covariance, and it makes sense that it's a function of the distance away from whichever one we want to compare to. So say n minus 1 to 1 is way further apart than 2 to 1, so it makes sense that 1 doesn't really affect n minus 1 quite as much as say 3 does. Here's an interesting example. Here I took alpha n equals floor of root n. So that means that 2 maps to 1 because the floor of root 2 is 1, the floor of root 3 is 1. Now square root of 4 is 2, so it maps to 2. And floor of root n stays to 2 until you hit 9, which is the next perfect square. So 4 through 8 map to 2. 9 maps to 3 and whatnot. So this is a slightly more complicated version, but notice that no matter which n I pick, there's still a path back to 1. So again, this is your visual representation that if there's a path back to 1, then we can see in a visual way why this theorem is true. Now, not all of them have to be monotonic. Here's a slightly more contrived example. And this generates a kind of funny looking graph here, but again, there's still a path back to 1. And here's all 4 of the examples together. So they generate a whole bunch of different shapes. Some of them have like a clear star pattern, some of this is just a straight up sequence, and some of them look just plain weird. But no matter which one you look at, you can see that there's a path back to that original, that first random variable, no matter which graph you're looking at. So these graphs produce a nice visual representation of that theorem. And it also shows you that the functions in this class are actually quite broad. There's another example that's extremely contrived with prime numbers. I didn't graph it here, but you're welcome to read the paper to check that one out too. So the functions don't have to be monotonic. They don't have to, they don't have to be just obvious. They don't even have to have a really nice formula. So again, see the paper for one that's quite a bit more contrived. Thanks for listening to our video supplement. Be sure to check out the paper for even more details if you're interested in the proofs. If you're viewing this on our site, the paper is right there. If you're viewing this on YouTube, then again, I'll link that in the description as well. As always, you can find your friendly but snarky mathematician on our website at theresearchcortex.com. Send us an email through the contact page, or you can check us out on Twitter at ResearchCortex or me at Mathpocalypse. We're always looking for feedback and especially ideas and contributions, so don't hesitate to reach out.